Hello, everyone. Welcome to another episode of Q&A about history of science and technology. And I see a number of questions saved up here. Um, let's see. Julia asks, do you think there have been scientific discoveries in human history that were genuinely correct, but disappeared because civilization lacked the intellectual ecosystem to recognize their importance? The answer is surely and definitively yes, on both small scales and larger scales. People have, whether it's, oh, I don't know, one that immediately comes to mind is things in medicine, where people kind of said at some point in the past, oh, all these systems are kind of integrated together, and that's sort of the whole person thing that you have to look at for some purpose in medicine. And then people said, no, 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 we're going to scienceify this, and we're going to figure out how to do sort of reductionistic science, and we're going to break it down into, diseases of this particular blood vessel and diseases of that and so on, and not and kind of ignore the fact that there's sort of a bigger systems kind of thing going on. And I think that's something where people sort of didn't quite have that the paradigm. Medicine in antiquity was much more of an integrative kind of discussion than in the post, scientific revolution, 1600s type period. This more, let's do the reductionistic thing, let's look at the micro pieces and so on, became much more the thing, sort of realizing how kind of complex systems like us get put together, which we're only just starting to really have any kind of serious sort of foundational scientific understanding of, something I've been working on quite a bit. That's but nevertheless, there are sort of ideas that emerge every so often, whether it's the gut-brain axis or these other kinds of things where actually it turns out the pieces fit together in much more elaborate detail than was understood on the basis of kind of reductionistic science. Exactly what the right methodology to think about that is something which I think still remains for the future, but it's something where people sort of had the right idea back in the day, and it got kind of crushed by kind of the reductionistic science approach. And so that's one example of that. I would say that in well, for example, in the idea of computation, the kind of idea of abstract computation, people were kind of nipping at that in the 1600s quite a bit. People like Leibniz, people who were working on these sort of philosophical languages for trying to describe things about the world in an abstract way and so on. There was sort of a lot of nipping at those kinds of things. But yet, the sort of whole conceptual framework that eventually led to the idea of computation just didn't exist at that time. I mean, the chain that was required to have it exist was, in retrospect, it looks like a lot of it wasn't necessary, but it sort of had to happen historically, I think, to get there. And that involved things like the idea of a mathematical function, the idea that you could say, first of all, people said, oh, first of all, I had to invent algebra. You had to have things like there's this thing, it's x squared. And for any x, you're computing x squared. But then there's the idea of that is just a function that goes from x to x squared. And you could pick up that function f and have it be this abstract thing on its own that you can start talking about. And that's really a thing that only became clear in the late 1800s. And that's the thing that you needed to have, this idea of sort of playing with functions in their own right, not with kind of the actual sort of raw material of x squareds and things like this. That I think was necessary for the invention of the idea of computation and this idea that you could do things where you essentially are creating functions, where you're having sort of data that turns into code, which is kind of the key idea that leads one to universal computation. But to have that idea, you had to have the idea that you could have, functions disembodied in some way, and that required that whole chain of things to happen. So that's another case. I think there are plenty of cases where kind of there's so much sort of belief about how things work that one ignores other possibilities. I'll give you an example that I've been much involved with, which is the idea of, is the universe fundamentally computational? Is it fundamentally made of discrete elements that follow discrete rules or not? Well, what happened was people sort of didn't know what the universe was made of for a long time. And then the 1600s came along, and folks like Galileo and Newton came along and said, look, we can use mathematics and eventually things like calculus to explain, to sort of miraculously explain lots of kinds of seemingly hard to understand phenomena about the universe, about the motion of planets and comets and things like this, and many other kinds of things. And so that got to the point a few hundred years later where people said that's how physics works. It works by following these kinds of equations, and maybe they're more elaborate equations, and they're the Einstein equations rather than the equations of Newtonian mechanics or whatever. But still, it's equations. It's equations all the way down. That's how the universe works. So in the 1980s, when I kind of started kind of really talking about the things in nature as being described computationally, it seemed very alien, particularly in physics. And in fact, that alienness, even at the beginning of the 2000s, it was still feeling very alien in physics. How could it really be the case that sort of underneath all of physics is this discrete computational thing? Don't we know it's all equations all the way down? And that's a thing where I would say what I noticed is between 2002, when my big book, New Kind of Science, came out, and 6 years ago, when we released the Wolfram Physics Project, there was a kind of quite an interesting change in kind of attitudes towards things. I mean, I think part of that change was the kind of decrease of self-esteem of the physics community, realizing no, things like string theory and so on weren't going to deliver the full story, but also the fact that sort of everything had been sort of more obviously, computation was a more obvious component as an important thing that particularly came in through interest in quantum information and so on. But that's a place where sort of those things had to be primed for, in the world at large, for at least lots of people to say, oh yes, that might make sense, as opposed to, no, we know it doesn't work that way, so to speak. So there's a few thoughts about that. I think that in terms of things where people had the idea and it just outright went away, I mean, sometimes it's well, okay, a good example would be, again, about computation. People like, well, particularly Ada Lovelace and Charles Babbage kind of supporting that, this is 1840s, kind of had the idea of universal computation, but it just didn't really have this support. I mentioned this thing about sort of functions that you can pick up and do things with and so on. It didn't really have that kind of support, and it wasn't until really the 1930s, 1940s, that 100 years later, more or less, that sort of really started getting legs and getting developed. And I think that's, I mean, there are many other examples where, I don't know, another one would be kind of the fact that there's things out in the universe that are kind of like what we have here. The thing that Galileo eventually in 1608 kind of when he looked through his telescope and saw, the moons of Jupiter, that was something where, gosh, there are little things that are orbiting Jupiter. Maybe that's like what happens with the Earth orbiting the sun and so on. But the notion that there could be, for example, sort of other planets around other stars and so on, the notion that there could be kind of an infinity of worlds a bit like ours, or a close to infinity of worlds a bit like ours, that was a thing people like Giordano Bruno had that idea, and people had like, no, that's not a thing, that can't be right. Now, part of that was because of the kind of religious tradition that said, humans are really special and we are sort of the only things like us, and it's kind of a shocking and terrible thing to say that there could be kind of other sort of things like us out there in the universe. We're not kind of the one and only unique kind of God-chosen thing, so to speak. I will say it's sort of interesting that in the ways that we are understanding kind of metaphysics from things we've done from our physics project and so on, I'm beginning to understand much more clearly the extent of sort of human specialness and the extent to which, in some sense, that sort of religious tradition of human specialness is correct, not in the sense that there aren't other planets out there like ours and there, chemical processes like the ones that happen on Earth, probably things like this. But the point is that the world as we see it, as we perceive it, the laws of physics that we perceive, the kind of aspects of the world that we choose to think about, are incredibly human-centered. And one could imagine thinking about the world with different senses and perceived in different ways, where it's a whole different world that one is perceiving. And but the world that we are perceiving, the world that we care about, is one that really is very much centered on us as humans and the way we happen to be. So in some sense, that tradition is quite correct, but sort of not for the reason of, oh no, there aren't any planets anywhere else, but more for the reason of it's if what we care about is sort of our perception of the world, then that's something that's quite specific to us. And if we say, well, let's be general, let's be more general, what you realize, and that's sort of the lesson of the Rulliad and the metaphysics around that and so on, is that as soon as you go away from that, you've kind of got nothing. You've both got everything and you've got nothing. There's no coherence to the picture that you have unless you're anchoring it around something specific, like the details of us humans. So again, it's sort of an idea that was kind of right for, in some sense, the wrong reasons, but maybe not really the wrong reasons. Then was kind of crushed by kind of the weight of sort of well, in that case, initially kind of sort of religious ideas, then this notion that humans might be special, that sort of crushed by the idea that science is general, and then one realizes that really isn't true. The general is nothing, and even the laws of physics depend on the way that we are. So a few thoughts about that. Let's see, sort of a related question from Tarek here. Is there a law governing how fast civilization can absorb fundamentally new ideas? Oh boy, I mean, people have sometimes said that the progression of science is measured in a sequence of funerals. That's a rather jaded view of things. But I think there is a dynamic that people sort of learn things and then they go and apply those things. And there has been, in the sort of history of the development of science, a lot of what's happened in the last, let's say, 100 years or so, is people go and they say, I'm going to be a scientist, and they go and they get a PhD in some area of science, and they learn a bunch of things for their PhD, and a large fraction of people spend the rest of their scientific career doing things that were basically the things that they were doing in their PhD. I think there was some statistic that half of all scientists are still working on the things that their PhD thesis was about. And so why does that happen? Well, people put all this effort into learning things. They make some investment there. It's kind of like, okay, I've made this big investment in learning this stuff. Let me take advantage of that investment. Maybe they don't have enough initiative to do something different. Maybe they do, but they think, this is what I've invested in, so let me get the benefit of that. And then 30 years goes by and they realize, gosh, I've just been working on the same thing all that time. And when something new comes along, people are like, look, I've got this big investment in this thing. I don't want to do this new thing. I'm just going to keep doing what I've been doing. It's working okay for me. Occasionally, things get dramatically disrupted, as people feel is happening in a bunch of areas with AI right now. If they get sufficiently dramatically disrupted, that people have no choice but to kind of look to something different, or at least many people think that way. But so I think one thing to realize is there is a time constant, which is career length. That is, people who get launched in a particular direction and just keep going in that direction, it's like if you're going to change that direction, you might think you have to wait for a new generation of people to start sort of new careers. So one of the things that's happened in the last probably, I don't know, 50 years or so, is that career lengths have increased. I mean, that's happened for some very sort of specific reasons and some general reasons. I mean, one is just life expectancies of getting longer. The other is that in the US, for example, since the 1980s, there hasn't been kind of a mandatory retirement age. So it used to be the case that in positions like being a professor at a university, It's like when you get to age, whatever it is, 65 or 60 or whatever it is, or something, it's like, okay, you're no longer sort of a working professor, you become an emeritus professor. There's a new generation that comes in. That kind of, as careers got longer and as sort of the politics of things changed and so on, that that kind of got erased in the US. It's still the case, I think, in the UK. I have friends who are heading for 67 years old, which I think is in Oxford and Cambridge is kind of still being enforced as some kind of at that age or out. Is that a good thing? Is that a bad thing? I don't know. It's it's more a question. I think there are a lot of detailed questions about sort of if there are many countries in the world where people say it's hopeless to become an academic. That the only way a new professorship shows up is if somebody dies, and they'll probably be in that professorship for 50 years. There are going to be no job opportunities in my area. So, that's sort of a bad case. But I think this phenomenon of, careers are getting longer. So insofar as people lock into a particular thing and keep doing that, the time constant for change is going to be higher. What drives change in the end? I mean, change is often driven by, well, sometimes it's driven by kind of uh, sort of external forces, like I don't know, the a new methodology comes into existence and people kind of realize, oh my gosh, we don't have to do all this stuff by meticulously counting this thing by hand or something. We just get a machine to do it. And people start doing it that way. And maybe there's some resistance to people saying, oh, you did it better if you do it by hand or something. But then over a fairly short period of time, there's sort of a disruption and that changes. I think in and sometimes there are things like there's suddenly great interest in some particular field as a result of something completely external. So, for example, there might be interest, well, in computer science, that's a good example of an area where the academic activity of computer science, which was fairly theoretical, suddenly got this sort of huge burst of interest from software engineering that really sort of changed the field and changed directions of it and so on. That was something sort of from outside the pure academic discipline. I mean, there are other cases of that. The same things happen with machine learning and so on. But there are other cases which have different origins, like climate science was something which was just sort of going and doing its thing. And as a piece of sort of meteorology meets sort of geology type thing. And then it suddenly became a politically important area. And then sort of it changed its character, got a lot of things injected into it. So it's these things that happen from outside the field. It's not because some big advance was made in the field. It's because something from completely outside the field comes and sort of increases its importance or something. That's another dynamic for sort of change, so to speak. But I think in terms of what it takes for things to sort of change direction, it works differently in different fields. When I was sort of doing physics for a living, one of the things people even started plotting was the length of time that different fads lasted in physics and the number of people in the physics community who were involved in that fad. So it had been the case, I don't know, let's say in the 1960s and so on, there were fads. The bootstrap approach, that's back in fashion now, but that had been a thing. The analytic S matrix approach, the this and that and the other. These were sort of fads that lasted, I don't know, 5 years, a bit more than that, and so on. Okay, by the late 1970s, there were fads that were lasting 3 months, and where people observed that the fraction of physicists who got into that fad had increased into the 70–80% range. And people realized at that time this is probably a really unhealthy thing. In other words, by the way, you see the same kind of phenomenon in the tech industry. It's like there'll be a moment when every startup wants to be a social media platform. There'll be a moment where every startup wants to be an AI hosting platform. All these kinds of things. And it's probably a sign. It's probably almost a theory of it that these fields kind of it's a sign that things are not going well when you end up with these very short, very intense fads where, for a moment, everybody wants to be a prompt engineer. For a moment, everybody wants to make, I don't know, an agentic harness for this or that thing. I mean, those are probably perhaps slightly unfair examples, but it's a thing where there are situations in which fields churn with this idea of it's new, everything's new, we've got to do this new thing, and everybody's got to jump into the new thing. And then there are long periods of time when there's very slow change. So I don't completely know how those dynamics fit together. It feels that this kind of the urgent faddery doesn't seem like a good sign for fields typically. Let's see. Samuel asks, what would it mean for science to end? Not because there are no more facts to discover, but because humanity has found the deepest possible conceptual framework. Well, it's an interesting question. I mean, I think with the things that have come out of our physics project, we have gotten to the machine code. We kind of know at a fundamental sort of almost metaphysical level, we know how the universe is put together. We know that we can think about it in terms of the Roolead, in terms of the limit of all possible computations. We know something about how we kind of sample that and so on. Does that mean science is over? We've got to the edge. We've got down to the bottom. We know what the fundamental components are. We know what the kind of atoms of existence are, and so on. Does that mean science has come to an end? The answer is fundamentally no. And the real reason for that is this phenomenon of computational irreducibility that I talk about a bunch. That is the phenomenon where even though you know the rules by which some system operates, knowing the consequences of running those rules is irreducibly difficult. Yes, you could just have your computer just run the rules step by step by step by step. But if you want to know what's going to happen in a trillion steps, it's going to take you a trillion steps of computation to find that out. You're not going to be able to say, oh, I know what's going to happen. I can immediately give you a formula for what's going to happen. I can immediately tell you what's going to happen without going through all that detail. So I think even though we know what's at the bottom, we think we know what's at the bottom in terms of how the universe is put together, there's sort of a very large chunk of irreducible computation between what's at the bottom and what we can now see. And in fact, when it comes to what is it worth us talking about, it's mostly worth us talking about these pockets of reducibility, these places where you can jump ahead and you can say what will happen, you can define kind of a natural law which you can describe, you can have something which sort of can fit in a human mind as a piece of narrative that humans can understand. There are these pockets of reducibility that are what give us our laws of nature, what give us the things that we do science about typically. And the question is, will we run out of those kinds of things? Even though we know what's at the bottom, the whole point is there's sort of this infinite collection of these pockets of reducibility that can be arbitrarily far away from the bottom. You can have to have assembled more and more and more pieces before it becomes the case that you're even able to see this kind of regularity. So I think the answer then is that science, even if we know what's at the bottom, science is never ending. It's the same with mathematics. With mathematics, if we have a field of mathematics, we at least imagine that we know the axioms for that field. We know that, in arithmetic, we can say for all numbers x and y, well, all things that we characterize as numbers, x plus y is y plus x, is the same as y plus x, and so on. We have these axioms. We think we know what the right axioms to start from are, yet we don't imagine that we get to say all the results of number theory. We expect, and we can even show that it must be the case, that there's an infinite collection of theorems that you can prove from those axioms. You never reach an end to that. The real question is, are the things that you are then able to figure out, the theorems that you're able to find, the results in the physical world that you're able to see, are they things that we care about? Or is it just, oh, that's a detail, we don't, that's not important to us. And that's a much more human question. And the progress of technology has typically been something where we probe more and more parts of the physical world. Things that we didn't think were, we said, oh, that's an amusing phenomenon, but we don't particularly care about it. Suddenly, it's the thing that lets you make, a better touch screen for your smartphone or whatever else. It's some weird electro-optical effect that was like, oh yes, that was discovered in, 1873, and nobody cared for 100 and something years. But then it became something that got lassoed into technology and where people do care about it. But there's sort of a question of will one get to the point where we've got what we need and we don't need any more from the physical world. We've mined all the phenomena we need from the physical world. We're just hanging out and doing our thing. I don't think that's the nature of the human condition, but I can't say for sure that that's impossible. I mean, certainly in human civilization, there are there are pockets where people say we're good. We don't need electricity, for example. We don't need whatever else. We're good. Sometime in the 1800s, we've got what we need to live a satisfied life. And, maybe that's something that would happen generally, in which case, yeah, people are going to stop being interested in discovering new things in science because they kind of don't need it. Or that would be, if it wasn't for aspects of the human condition that lead us to always be curious, hey, how does this work? What else can we do? There's a question, I suppose, of whether, what are these levels of thresholds? There's science that we care about. Oh, we figured out a bunch of things about materials, science of materials. That's been an important thing for lots of technology we've built. Let's take particle physics as an example. We know that it might be the case that the structure of atoms, nobody would care. But it turns out, nuclear energy is kind of important, and that requires knowing about the structure of the nucleus and protons and neutrons and so on. But if you're into particle physics, there's a giant zoo of other particles, the strange particles, the kaons, the lambda hyperon, the cascade hyperons. These are all particles that I was very interested in these when I was a kid. There's a whole zoo of hundreds of these kinds of particles. They don't last very long. They might have a lifetime of 100 millionth of a second or something. They're produced in particle accelerators. They disappear. It's like, do we care about the omega minus particle? Or is it just something which is like, kind of nice to know, but we don't really care? It may be the case that the distance between sort of the way we are as humans and the omega minus particle and its, rapid decay. Well, how fast does it decay? Maybe 10 to the minus 6, 10. Let's see. I'm going to guess 10 to the minus 11 seconds, but I might be wrong about that. But in any case, gone in an instant, produced in a particle accelerator and rapidly disappears. Is that something that we're going to have a sort of human technological application for? My guess is that's pretty far away because the sort of scale of stuff that for which that is relevant is far away from a human scale. Give you an example, it's a little bit closer at hand, the muon, another part of the particle zoo, particle very much like the electron, but 206 times heavier than an electron. So there's a whole bunch of muons that are going through us all the time. They're produced by cosmic rays. Cosmic rays are things like protons and so on that come from the sun. That's the most common source of them. They hit the top of the Earth's atmosphere. This high energy proton is coming in. It collides with some atom in the atmosphere, and it produces a whole shower of particles. And a bunch of those particles eventually turn into muons. And muons, in their sort of natural habitat, last about 2 microseconds, 2 millionths of a second. When they're going very fast because of relativity, there's time dilation, and they last longer. But basically, the muons are gone in a couple of microseconds, usually. So the question is, do we care? Is there anything of technological relevance, of human relevance about muons? Or are they just a thing that, like, that's an interesting piece of science, piece of particle physics, but it's irrelevant to us? Well, there's slowly starting to be things for which muons are relevant. So you can use them to kind of, if you want to sort of do tomographic X-raying of the Earth, so to speak. Like, let's say you've got this pyramid and you're trying to figure out, is there a hidden chamber inside the pyramid? Well, you could go and look and see whether the cosmic rays that are coming in and hitting the pyramid, whether there seem to be sort of more cosmic rays than you would expect, because you would think more of them would have been absorbed unless there was a big hole in the middle of the pyramid. That's an actual experiment that was done, I think, in the 1940s, I think, soon after cosmic rays were discovered. but that's in a sense an application for muons. There are applications that involve, oh, I don't know, is this container that's just arrived at some port, does it contain, uranium or something? Does it contain some heavy elements? Well, you can potentially tell that by doing muon tomography, or can you find, hidden archaeological or tunnel structures underground? Well, maybe you can do that with muon tomography and so on. So it's a case where this thing that seemed like it was just a fun fact in science suddenly starts getting lassoed into something that has human relevance. You might say some of these other particles, like the pions and kaons and things like that, which last a very short time, and it's like, well, they're interesting, but are they human relevant? Actually, there are cases for radiation therapy for cancer and so on, where some of those things are potentially very important because they have different characteristics in terms of going into human tissue, and they're just sort of going in and they're not really doing much damage, and then they kind of stop in a very short region and dump all their energy and kill the cells you want to kill, or whatever else it is. So again, kind of a funny way that one might not have expected that the kaons become important type thing. But that's the question, is whether there are pieces of science that are so disconnected from the human experience that we can say, well, that's kind of interesting, but we don't, it's not going to have human relevance. You could say that about a lot of cosmology. It's like the details of how, when did the first galaxies form, and how far does, what's the gravitational binding of this cluster of galaxies or whatever else. It's like, that's not of human relevance. That's science, but not humanly relevant. And I think that's sort of a question of what drives science, and does there come a point where people say, we know what we need to know, it's all good, we don't need to know anymore. Now, as I was mentioning earlier, there are times in history where people said, we don't want to know that piece of science. We don't want to know that we might not be unique in the universe, or we don't want to know this or that thing about how some aspect of sort of the deconstruction of the human condition and so on. And I think that's another issue, is are there places where there are kind of boundaries where one says this just isn't a very good idea? So a good example in modern times is, should one create viruses that could wipe out our species? Might be hard to do, one doesn't know how to do it, but does one want to push in the direction of doing that? One might argue that's simply a bad idea. And so there might be science that one could learn from finding more virulent viruses and so on, but it's like, let's not do that. That's just not a good idea. And so the question of sort of where are those boundaries is an interesting question. I tend to think that it's sort of if it's easy to do, people are going to do it, whether you say you shouldn't do it or not. And I think the sort of the story of, for example, nuclear weapons proliferation is one where it's just not very easy to do. It's like a very complicated supply chain and so on. It's not like you can just go to the corner store and pick up a lump of uranium-235. So which is a little different. For example, in some of these biology areas, there's more concern because it is potentially a lot more accessible to do things which are sort of bad idea type experiments. Let's see. Ratius is asking, is string theory over or not? String theory has many lives. Not the 9 for a cat, but it's had at least 3. I mean, string theory originated in the early 1960s, no, actually kind of the beginning of the 1960s, where, well, it's a complicated history. And part of the history had to do with just, how do we do quantum mechanics for things that aren't point particles? Oh, we can do it for these string-like things. That was sort of a mathematical physics play. Another piece of it had to do with lots of kinds of particles were getting discovered in the late 1950s, early 1960s. And there was a question of sort of, how do we understand this zoo of particles? What became clear in the end was that quarks were kind of the thing inside all of them. And that was sort of a theory that was proposed in 1964. And but sort of interestingly, and it's kind of a funny sort of connection of what's going on in the world versus what's going on in science. There was this idea that sort of the hierarchical notion of its quarks at the bottom and from them make made all the particles get made didn't really fit with the kind of social kind of prejudices of some physicists. So very much centered around Berkeley, California, kind of a very hotbed of kind of social activity, particularly at that time, was kind of this idea, no, 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 let's not have hierarchy. There are no king particles. Let's have everything be democratic. Every particle is kind of as fundamental as every other particle. That led to this kind of bootstrap idea, which kind of led to sort of in the mathematics of it, it kind of led to things which were one of the early versions of string theory. So string theory was originally something relevant to the study of strong interactions and the presence of all these particles and so on. That was kind of existence number one. Um, the It then kind of, well, it came back several times, and then it kind of got connected with supersymmetry, which is a whole another thing which was originally introduced as kind of a sort of a mathematical kind of completion kind of idea, um, but then sort of got its own merged with the mathematics that had been done there. And then in the 1990s, it became clear that the mathematics of string theory sort of connected to lots of other kinds of things, including questions in pure mathematics and things like the theory of knots and so on, that didn't really have any obvious business to be connected to these kinds of questions that were coming up in physics. But things were sort of elegant enough that it turned out these sort of natural questions in mathematics mapped into these sort of natural questions about sort of things like string theory. Well, the thing was that as a sort of practical model of, oh, does this represent, particles in the universe, things kept on going wrong. First it was the case that sort of vibrations on this string would end up going faster than the speed of light and cause all kinds of weird problems and so on, unless the universe happened to be 10-dimensional or maybe 26-dimensional. And then it's like, well, where are those extra dimensions? Well, there'd actually been a theory from the 1930s that sort of already talked about the possibility of sort of extra dimensions being all curled up in little balls and so on. And so that got kind of brought out as a way to save the day for those kinds of things. And then there were all kinds of sort of, well, somewhat predictions of, oh, there'll be all these other particles found. None of those particles were found. And then there were all these things about how you'll be able to compute things more easily in string theory. And string theory is sort of, it's not like the actual physics of quantum quarks and gluons and so on that we know, but maybe it's in the same general class of things. Maybe from string theory, we can learn things about computing things in sort of more practical areas of physics. That's still an ongoing possibility and still something people are studying. But it wasn't quite a slam dunk, a thing that worked as one might have hoped. So I think, realistically, the sort of, as is so often the case, it was kind of a little bit oversold as, where it's going to be really hard, but we're going to get there. And then it's actually the there doesn't actually make sense. It's not really, doesn't really answer the questions we want to answer. And I think it's sort of, my own feeling is that string theory is probably an interesting limit of a bunch of things that we're understanding about sort of what the machine code of the universe is like, but it probably isn't the case that's most relevant for looking at the universe as it actually is. It's probably mathematically interesting, and more work should be done on it. But I don't think it's sort of a mathematical branch that is informative and probably rather elegant and aesthetically pleasing, but probably not the branch that is going to lead us to the most practical things in terms of understanding physics as we know it right now. By the way, I think this whole business about how sort of there's the dimensions that we know about, the sort of 3 dimensions of space and so on, and like, is there anything else? Well, we kind of know that we can think about in gauge theories and physics and so on, we can kind of think about this notion of gauge as being sort of another coordinate. And well, we're coming soon is some way of understanding that in terms of our models of physics, which I think is going to be rather exciting. And we're going to be able to see that just like you can kind of move around in physical space, you can kind of move around in gauge space. So to give one rough physical version of that, when you think about voltage, you say, voltage is kind of, if there's a voltage difference, it'll push electrons from sort of the high voltage to the low voltage or whatever. It's actually the other way around, but it depends on how you look at it. But in any case, it's voltage differences are pushing things. But the question is, what's the actual value of the voltage itself? Well, that's kind of an arbitrary thing. You can run it up and down. And I think there's a sense in which, just like you can move around in space, sort of choose to move somewhere in space, you can kind of choose to change this voltage. And that's sort of a somewhat analogous thing, kind of direction of things in our physics project that I think come from that kind of intuition. But just a few thoughts about that. Andre is asking, is there experimental evidence of string theory? No. I mean, there were various things where people thought, let's go look for this, and none of those things were found. Now, string theory doesn't tell you, this particle will have this particular mass, go look for it in this accelerator. It's more general than that. But the funky phenomena that you might think were there, like these supersymmetric partner particles and things like this, didn't get found. I think it's at some point there's also a complicated story of just what does string theory really say? I mean, it's like you could ask, is there experimental evidence of calculus? That's kind of a silly question. It's not the right kind of question to ask. Calculus is a methodology for making models of things. You can ask, is there experimental evidence for the particular model of planetary motion that can be formulated in terms of calculus? But if you say, is there experimental evidence for calculus, it's kind of an asking about the wrong category of thing. And I think to some extent, string theory is a bit like calculus. It's more a methodology than it is something which should be anchored into, oh, there's this particular specific prediction about some particular particle. Okay, physics was asking, do you remember the so-called November Revolution, the discovery of the J psi particle? What was being done in physics? What was being in physics at that time like? Yes, I absolutely remember that. That was in late 1974, I think. And I was 14, 15 years old. And I was very much following these things. And what happened? Well, so there were, let's see what I can remember here. There had been, so particle physics had been sort of this field that had really been kind of born out of kind of the follow-on from the Manhattan Project of kind of the US government was prepared to invest a bunch of money. Physics seemed important. Particle accelerators were built. People were smashing protons together at very high speed and so on. And lots of things were happening. Lots of new particles were being discovered. But it was a bit messy. It was kind of like there were these different approaches and so on. Maybe I should give a little bit of backstory. So sort of atoms, particles, electrons, things like this. Those were things that were discovered in the early part of the 20th century. By the 1920s, the mathematical formulation of quantum mechanics existed, quantum field theory existed, the kind of how do we describe how electrons and photons interact in electromagnetic processes. That was kind of the basic idea for the theory was known in the 1930s. There were all kinds of mathematical issues in being able to work things out from that theory. Those got resolved in the 1940s, 1950s, and so on. So 1950s, quantum electrodynamics, the theory of electrons and photons, that was in pretty decent shape. That was like, it's a theory, it's working, et cetera, et cetera, et cetera. Then there were other kinds of phenomena with particles. There were strong interactions, the interactions that hold nuclei together. They were not understood at all. It was some description existed of them, but it's like, can we calculate things about strong interactions? No, not at all. Then there were the weak interactions that lead to nuclear beta decay and have things to do with neutrinos and so on. Neutrinos were discovered in the 1950s, and and it was also discovered that weak interactions had the strange feature of being parity violating, in the sense that sort of, well, what that means in practice is that there are left-handed neutrinos that have their sort of direction of spin anti-aligned with their direction of motion, and there are right-handed neutrinos, but you don't find, at least not very many of them, right-handed neutrinos. Because neutrinos don't have zero mass, there's a slight change of that. But basically, this sort of violation, the left-handers are not there. There's sort of, it's only left-handers and not right-handers and so on. That was something people didn't expect. That was a feature of weak interactions discovered in 1956, I think. So anyway, coming into the beginning of the 1960s, strong interactions not understood, weak interactions kind of weird, electromagnetism pretty well understood using quantum field theory. Okay, quantum field theory and the method of Feynman diagrams and so on, which assumes that the interactions are fairly weak, and you can kind of just say, oh, there's one photon exchanged, or two, or three, or four, but you can, by the time it's four photons, the likelihood of that is really low. That approach, so-called perturbation theory, just didn't work for strong interactions, because it's like, oh, there's one pion exchanged, but there might be 17 pions exchanged, and that happens at sort of about the same rate as one pion being exchanged. So we can't do this kind of mathematical series expansion and so on. So people didn't know what to do with it. And this thing called the S matrix that had been invented in the 1930s was just a thing that said, imagine particles are coming in and they're colliding with each other and then they go out. Just say there's an S matrix. There's a mathematical object that describes the transformation from the incoming particles to the outgoing particles. Let's study the mathematical properties of that object, the S matrix. And it has various properties of being smooth in certain ways. It has various symmetries and so on. And it's like, what can we get from understanding the S matrix as a piece of mathematics, as a piece of functions of many complex variables and so on? So the two things coming into the 1960s, the kind of two approaches, one was from quantum field theory and kind of like we can look at individual particles and so on. The other was from S matrix theory, which was like, we've got to just look at the whole thing as a big ball of, sort of a big single ball of stuff. From S matrix theory came eventually string theory. From the kind of quantum field theory direction, well, the next thing that happened, 1964, the idea of quarks. But it wasn't really clear. Quarks were very confusing to people because, in a proton, there's supposed to be three quarks. Okay, show me a quark. Well, you can't get them out of a proton. And people would bash protons and say, can we get a quark out of this proton? Well, no, it doesn't come loose. It's always confined in the proton, it seems. But that seemed like almost a philosophically wrong idea, that we're saying there are these particles, but you'll never see one. You'll never be able to pick one up. And so it wasn't really clear what that meant. So in the 1960s and going into the beginning of the 1970s, it was still like, are quarks real things? Are they philosophically meaningful, et cetera, et cetera, et cetera. 1971, there were a bunch of experiments done of shooting high energy electrons into protons. And what you might have thought was, oh, there's this proton. Protons are pretty big by the standards of particle physics. They're 10 to the minus 15 meters across. Electrons, nobody knows how big they are. They seem to have zero size. I think they don't have actually zero size, but they're small compared to protons. You run an electron, you shoot an electron at the proton. It's like, is the proton this big mushy thing and the electron just goes straight through, or does it hit a hard bit in the middle? Well, back in the 1910s, Ernest Rutherford had done these experiments where he shot alpha particles at atoms. And what he found was most of the time the alpha particle just goes straight through. It's just sort of empty space in the atom. But occasionally the alpha particle hits a hard bit and gets sort of scattered at a high angle. And that's the discovery of the atomic nucleus. Atomic nuclei are very small compared to atoms. There's a small hard bit in the middle of an atom. It's 100,000 times smaller than the atom. So most of the alpha particles just go through the empty space, so to speak, but just a few hit the hard bit. Okay, that same thing got repeated in 1971 in what was called deep inelastic scattering, which was shooting electrons at protons, and most of the time the electron would just sort of go straight through. It's just sort of a blob of of low density stuff in a sense in the proton, but every so often it would hit a hard bit and get scattered at a large angle. What were those hard bits? My friend Dick Feynman called them partons. And my also friend Murray Gell-Mann, who was the inventor of quarks, referred to partons as putons. Those two had quite a complex relationship, let's say. But in any case, so 1971, discovery of some hard bits, a lot of confusion about what was going on there, a lot of kind of mathematical structure being created that was, well, very empirical kinds of things. The various kinds of scaling laws of talking about how, if it's scaling laws are all the time. You hear about scaling laws in AI systems. There were scaling laws for what happened in deep elastic scattering in 1971, 1972, and so on. Okay, so there was something up inside protons, and maybe these partons were in fact quarks. That turned out eventually to be the case, but that wasn't clear at that time. It was still like, we don't really know how this works. Then the other thing that was sort of one of the other, the next big thing that was happening was a bunch of new particle accelerators were coming online. There were a few that had been, these particle accelerators were dotted around the world. So the CERN, European Center for Nuclear Research in Geneva, that's sort of a big thing created in the 1950s as a big sort of international collaboration. That was a big place where there were a bunch of particle accelerators, progressively bigger particle accelerators. Fermilab in the US, outside Chicago, to the west of Chicago. Another place which was sort of the big sort of US, one of the big US places that sort of really grew up, I would say, in the 1970s. In the US, also Brookhaven National Lab on Long Island, then the Stanford Linear Accelerator Center in California, in the Bay Area. These were sort of as I say, dotted around, there were particle accelerators. And then there were some others. There was some in Russia, in Novosibirsk. There was one in Frascati in Italy. There was a small one in England. There was one in Saclay in France. These were sort of, these things eventually got consolidated because as they got bigger and cost more billions of dollars to build, there were fewer and fewer of them built. But back in the beginning of the 1970s, there were several. And I remember the big thing that was happening was electron-positron colliding beams. So normally you can accelerate a particle and you have this whole big bunch of accelerated particles and you smash them into a target. And then things come out behind the target, so to speak. But what was figured out was how to make colliding beams, where you could have in the magnets, you could have beams circulate inside these particle accelerators, and they would circulate in opposite directions. And one very convenient thing is that if you have a magnetic field that's kind of keeping particles going around in a circle and maybe accelerating them, if it's accelerating electrons to go one way, if you put in positrons, anti-electrons that have opposite charge, those go the other way around the exact same collection of magnets. So there were these colliding beam machines made with electrons and positrons. There was one in Frascati in Italy. I think the one in Novosibirsk was also running. And there was one called SPEAR, I think, which was at the Stanford Linear Accelerator. And the Stanford Linear Accelerator was an electron accelerator. These other things, that one was mostly get electrons to go in a straight line, but they had a little storage ring at the end where they would have circulating electrons and positrons. So people were crashing electrons and positrons into each other at a high rate of speed. The main sort of numbers to know were the so-called center of mass energy. And the center of mass energy was like 2 GeV in the units. So one GeV is roughly the rest energy of a proton. So 2 GeV was a certain energy you could get certain things to happen. When you had 2 GeV of energy, you would be able to produce kind of 2 GeV of mass of particles. So you get a bunch of pions. Pions weigh about a tenth the mass of an electron. So you get a bunch of pions coming out and so on. So there was stuff happening in the sort of 2 GeV range, and then gradually things were going up. The energy was going up, 3 GeV, 4 GeV. Okay, so this was 1974. The thing that was there was something weird seen. So there was a calculation of I haven't thought about this in decades. It takes me a little while to remember all of this. The question was, what was the total probability of electrons and positrons interacting? The so-called electron-positron total cross-section. It's called cross-section because it's like you're shooting at something, and you ask, if you shoot this point thing at that target, what's the chance that you hit the target? Well, it depends on how big the target is. So the cross-section is roughly, you're aiming at a proton. If the proton is such and such an effective size, then you'll hit it with some probability and have an interaction. Okay, so electrons, which remember are supposed to be point particles, there's still some effective cross-section. It's as if the electron is a certain size with respect to how often kind of things, you kind of get an interaction with the electron. Okay, so the electrons and positrons can interact through purely electromagnetic interactions, just with photons being exchanged and so on. There's a certain rate of that. What's it called? I think it's called Barber scattering. Is the calculation. There's Barber scattering and Moller scattering, if I remember correctly. One of them is electron-electron scattering. The other is electron-positron scattering. And quantum electrodynamics allows you to calculate the rate of those interactions. Okay, all good. Now the question is, when electron-positron interaction happens, and the electron and positron then, in a sense, annihilate each other, they produce a virtual photon, which kind of carries a whole bunch of energy, and that energy's got to turn into something, and it turns into a bunch of particles. And those particles will be like a pi plus and a pi minus. There'll be lots of different kinds of possible particles. The higher the energy, the more of those particles can be produced. Okay, what's the total rate at which that happens? Can one calculate it? So at very low energies, very hard to calculate. As the energy went up, there was a calculation that was based on the existence of quarks that said the total cross-section should be this value. You basically can generate an up anti-up quark, a down anti-down, a strange anti-strange. That's it. There's a certain number of those things. You can calculate the total cross-section for electron-positron annihilation going to so-called hadrons, strongly interacting particles, which are the things that are made of quarks. So you could just calculate what should be the total cross-section. There was a value based on the existence of those 3 quarks. Okay, so now we're in 1974, early 1974, and the cross-section starts going up. Was it correct? People didn't really trust the results from Novosibirsk in Siberia. They didn't really quite trust the results from Frascati in Italy. They kind of trusted a bit more the results from the Stanford linear accelerator and so on. But there was kind of a bubbling, what's going on? Something weird is happening. Now, I have to say, effects in particle physics, it's very hard to do these experiments. There would be effects that happened and then they would disappear again. There were all kinds of, oh, there's this really weird thing that's happening. Oh, whoops, it doesn't really happen. So people weren't sure whether this rise of the electron-positron cross-section around 4 GeV was a real thing or not. Okay, so that was all going along. Now, okay, another thing I should explain is when you discover a particle, how do you discover a particle? Well, one thing you can do is some of the early particle discoveries were made when they weren't using accelerators, they were using cosmic rays. But when what would happen, and this also was done with accelerators, you would have these stacks of emulsion, for example, emulsion like the stuff that was early, old photographic film. And when a particle, high energy particle, goes through emulsion, it basically is like a photon going through there, and it sort of exposes the emulsion in some sense. So you get a track in the emulsion. So an early thing you could do, and people did this from cosmic rays, they would send them up in balloons to get so that they were more high energy particles that hadn't been stopped by the atmosphere. They go on mountain tops and so on. they would expose these emulsions, and they would look at the emulsion, under a microscope. They would kind of slice through different layers, and they would see these little tracks. And those little tracks were particles, and then they would see this track leads to these other tracks and so on. You're trying to figure out the interactions of these particles, very much laid out in emulsion, so to speak. And a bunch of particles got discovered that way. Particles with lifetimes of 10 to the minus 10 seconds, 10 to the minus 8 seconds, things like this. The so-called strange particles were discovered that way in the 1950s and so on. And the pion had been discovered that way in the 1940s, so the muon, all these kinds of things. And by the way, that was a very early use of sort of machine learning. I remember when I was, this must have been the mid-1970s, first of all, sort of this was a very high-tech thing. People would be, they would have these big photographs, essentially photographic plates, and they would have in different layers, and they would have all these tracks. They were trying to say, is there a track there? And there were folks who were kind of sort of people whose job it was to just look at these emulsion stacks, very carefully and say, was there a track? Was there a track? Hey, that's a pion. Hey, that's a new kind of particle, whatever. So that was kind of a thing. And then people started trying to do image processing and essentially machine learning to find those tracks. And that was a very early use of those kinds of things. That's now been developed much more dramatically in modern particle physics experiments, but that was already happening in the 1970s. Anyway, so particles this is a little bit of particle physics stuff, but particles so I mentioned the muon decays in about 2.2 microseconds, 10 to the minus 6 seconds. The things like the kaons decay in 10 to the minus 8 seconds, or another one, 10 to the minus 10 seconds. These different ranges, the pi zero decays in 10 to the minus 16 seconds. There are these kind of batches of particles that decay in different times. Those different decays are associated with different underlying processes. So the ones that have lifetimes of 10 to the minus 6, 10 to the minus 8, 10 to the minus 10, those decay through weak interactions. Those decay through the same mechanism as associated with the production of neutrinos, et cetera, et cetera, et cetera. So that's one bucket of things. Those things you could discover by looking at one of these emulsion stacks, and you could just see a little particle track there. Okay, so then there's another range of particles, 10 to the minus 16 seconds or so, decay through electromagnetic processes. They're a little bit more difficult to detect. And then there's a whole bunch of particles that decay in 10 to the minus 23, 10 to the minus 24 seconds. You can't see a track for that. So you have to have some other way of detecting the existence of those particles. You don't get to say, oh, it's, I see it in my emulsion, for example. Okay, so those are the particles that decay through strong interactions, through the things that are the kind of interactions which we now know associated with quarks and gluons and quantum chromodynamics, QCD, and so on. But anyway, those are all 10 to the minus 24 seconds, give or take. How do you detect a particle that only lives 10 to the minus 24 seconds? Well, the answer is, if you shoot two particles in, and those particles, most of the time, they just sort of bounce off each other or whatever else. But maybe those particles form another particle that only lives 10 to the minus 24 seconds, but they form that other particle. It's a definite particle with a definite mass. So what happens is, when you look at the scattering cross-section, the probability that particles interact, and you look at that as a function of energy, then when there is it's usually called a resonance particle, when you form this particle that is this thing that happens to exist, albeit for 10 to the minus 24 seconds, there's a big peak in the cross-section, in the probability of interaction. So the way that most of these particles discovered in the 1960s were discovered was through looking at the interaction probabilities as a function of energy and saying at that energy, there's a bunch more interaction probability, and that means there's a particle with that mass corresponding to that total energy that's being produced. So, there's a whole zoo of these things. I don't know, the rho particle, rho meson, with a mass of 770 MeV, so 0.77 GeV, about 3/4 of the mass of a proton. That was discovered in this way. There's a there's a kind of a peak in the probability of particles interacting at a certain energy that corresponds to the mass of the rho particle. Now, the way the mathematics works out, maybe this is too detailed, but the when there's an interaction like that, there is both a peak in the chance of interaction, and also the fact that an interaction happens slows in a sense, you have particles coming in and they act like waves and they're coming in with a certain sort of frequency of the waves. And then they undergo one of these interactions that forms another particle. That leads to a phase shift, a shift in the phase of the wave. And what happens is that's another thing you can detect in when you do these particle experiments. But what happens is that the shorter the lifetime of the particle, the more fuzzed out the peak associated with this interaction probability is. So by the time you're down at 10 to the low 10 to the minus 24 seconds, it's a very fuzzed out peak. It's no longer something where the rate of interaction is very high in this tiny range of 100 MeV, 0.1 GeV or something. It's fuzzed out over half a GeV or something like this, where the interaction probability is increased. So particle discovery, particle hunting was kind of a hunt for bumps, a hunt for little peaks. And sometimes, quite often, there would be, people would say, was there really a peak there or was it not really a peak? Is that really a particle? Is it not a particle? I remember the particle called the A2, which has a mass of, can I do this? Either 1300 or 1400 MeV. So maybe 1420, maybe? I'm not sure. I'm afraid that's gone from my memory. But that's from I don't think I've thought about it since the mid 1970s. So that's a long surviving neuron or synapse or something. In any case, the A2 meson was the so-called split A2. It seemed to have two peaks, and that was a big production. It's like, why does it have two peaks? Is it some special new kind of physics? It was probably an experimental mistake, or it was two quite different particles. I'm not sure. But in any case, so there's a lot of peak hunting, but some of these peaks were very fuzzed out and so on. Okay, now we get to November of 1974. Okay, and we're looking at electron-positron interactions. There's been this increase. People don't know what it's due to. Lots of different theories. I had a theory which turned out not to be right. It's actually the last time I've had a physics theory which didn't turn out to be right was when I was 14 years old. So I'm happy about that. But the record since then has been rather good. My theory at that time was that electrons, much smaller than protons, but nevertheless have the same kind of interactions as protons do, but just at a much smaller scale. Actually, I think that theory is probably right, but the scale is utterly off relative to what one was observing at that time. In any case, so, people had theories, nobody really knew what was going on. Then suddenly a peak was discovered in a chap called Burton Richter, I think, was the head of that team at Stanford that discovered a peak in electron-positron interactions at 3.1 GeV. A very sharp peak, much more dramatic than the peaks people were kind of fighting over in other places. Meanwhile, at Brookhaven National Lab, Long Island, in proton experiments, another slightly different way that the experiment was done, proton collisions, actually protons hitting a target, and then producing sort of resulting particles, some of which decayed, and you could reconstruct the mass of the particle that was decaying, and another peak at 3.1 GeV. That was a group led by a chap called Sam Ting. So these things happened basically at the same time, and there was sort of a grand announcement of the group at Brookhaven called the particle the J, the group at Stanford called it the Psi. I think I'm getting it the right way around. Yes, I am. And so it eventually became called the J Psi because the two groups kind of were duking it out for what the name of the particle should be. Okay, so what the heck was that thing? And the people didn't know. It was really dramatic and surprising. And it's like nobody's seen a really clear signal of a new particle in, at that time it had been more than a decade since such a thing had been seen, of a dramatic new particle. What on earth was it? Well, okay, there had been a, my gosh, we're dredging things from my memory here. Um, uh, in so remember I talked about quantum field theory. Quantum field theory had not really been successful in talking about strong interactions. But there was a theory that was, okay, if quarks really exist, how would quarks interact? And there was this theory that emerged from multiple people at the beginning of the 1970s that was QCD, the theory of quarks and gluons, where the idea was that just as electrons have electric charge and they have interactions that are associated with photons, then similarly, quarks might have a color charge, a different kind of charge, which would be where the interactions associated with color charge would be associated with gluons. And one of the sort of kicker weird things would be, whereas photons don't interact directly with each other, gluons would interact with each other. Okay, so that was a theory that the sort of mathematical theory of quarks and gluons sort of generalizing quantum electrodynamics was something that had come out of a thing called Yang-Mills theory, invented by C.N. Yang and Robert Mills in the mid-1950s as kind of a mathematical theory. And that mathematical theory was originally applied to something quite different in strong interactions. But it was kind of a theory of how you could have sort of things that were sort of generalizing electrodynamics with different kinds of particles and with different with the color charge, unlike electric charge, where it's just like there's a voltage. It's a single number that represents the voltage. If you did that for color charge, you'd have to have three different kinds of voltages, so to speak, that you describe. It's a more complicated setup. It involves the group SU3 rather than group U1 if one's into mathematical physics stuff. In any case, the basic point was Yang-Mills theory existed. It was applied to quite different things. Beginning of the 1970s, and there was a collection of people, and I don't completely know that history. And I've wondered about that history, and I knew all the people, but nobody was kind of saying, I invented QCD. Well, Murray Gell-Mann sometimes said that. A guy called Harold Fritsch said that, I think. But there are a number of people who said that, but it was never very clear to me how this had emerged. It was kind of it sort of just sort of blobbed out that this would be Yang-Mills theory, generalizes quantum electrodynamics, quarks exist. The idea of color for quarks. Oh yes, I should explain something else. That was an idea, I think was a chap called Ollie Greenberg, I think, who came up with that idea. If I remember correctly, that was in the 1960s. There was sort of a mystery about quarks because there's this principle in quantum mechanics, the exclusion principle, that says you can never have two particles in the same place in the same state. And that's what kind of determines how chemistry works. The fact that there are electron shells and very different chemistry of different chemical elements is a consequence of the fact that when you put more electrons into an atom, they can't be on top of each other, so to speak. So the same phenomenon can happen with quarks. And it was sort of a mystery that there could be particles that had multiple quarks that seemed like they were the exact same quark in the same place. Like a proton has two up quarks and a down quark. By the way, in those days, they weren't yet called up and down quarks. They were often called P and N quarks, which was rather confusing. But anyway, in any case, and so I think it was Greenberg kind of had this idea, maybe the two up quarks that shouldn't be in the same state at the same time weren't really the same. Really, maybe they had different colors in some abstract sense of color, and that was what explained that. And then when the idea of sort of color charge as being like electric charge pulled in with Yang-Mills theory gave one quantum chromodynamics. Okay, so by that time, quantum chromodynamics was sort of a known theory, but nobody really cared. It was just sort of a mathematical theory. Yes, you can do this. then 1973, several characters who I know quite well were involved. In 1973, the phenomenon of asymptotic freedom was discovered in QCD. So roughly what happens is that when you have a particle that has a certain charge, it'll have a cloud of particle-antiparticle pairs around it, virtual particle-antiparticle pairs that kind of shield that charge. And so if you kind of are probing the thing more and more, you're kind of drilling in and seeing what's the real thing inside, but inside that sort of coat of other things. How does the charge effectively change? Are the interactions getting stronger or weaker as you probe harder? Turns out in quantum electrodynamics, there's a small effect that makes the kind of interactions get stronger as you probe harder. Okay. And that's characterized by a thing in theory of the renormalization group theory, a thing called the beta function. Okay, the beta function was something invented in the 1960s. Actually, Murray Gell-Mann and Francis Lowe were some of the inventors of the beta function, except they called it the psi function. And it's an unforgettable conversation that I had with Murray Gell-Mann once, in which I was talking about the beta function, and he's just looking confused and like he doesn't understand what I'm talking about. And eventually, it goes on long enough and long enough and long enough. And eventually he says, you mean G times the psi function, which of course he knew it all along. He was just kind of being difficult, as he often was. But in any case, this thing, the beta function, big thing, that was the thing that determined, would this interaction strength get weaker or stronger as you drill in, how much stronger would it get, how much weaker would it get, and so on. For quantum electrodynamics, the beta function is positive. The interactions get stronger as you drill harder. Okay, in 1973, two young physicists did calculations of what the beta function was in QCD. There was a person called Frank Wilczek and a person called David Gross, both at Princeton. There's a person called David Politzer, who was at Harvard, and was kind of connected to his advisor, who was a chap called Sidney Coleman. So these people, and I mean, I know all these people, and I think it's still a source of great kind of, who knew what when. Actually, another person involved was Gerhard Hooft, who had also done this calculation, apparently. Okay, nobody thought the beta function could be negative. It's just like, that can't happen. I think maybe at Hooft had done the calculation and had found it was negative, and it's like, that can't be right, or who cares, or whatever. Okay, what was realized at some point in 1973 was actually the beta function could be negative, and that was very important. And why was it important? It was important because it said that as you drill harder, the interaction strength gets smaller. So in other words, if you do a higher energy scattering experiment, you should see something which is less and less strong interaction. So what that suggested was that if you just sort of gently bump an electron against a proton, it's just going to say this proton is really complicated inside. There's a lot of strong interaction going on. But if you really ram that electron in at very high energy, then it will be kind of drilling harder, and it will then not see such a strong interaction, and it will see something which looks much more like kind of a quantum field theory, just interacted once type thing. Okay, so that was, people in 1973 were beginning to have the interpretation that deep inelastic scattering, the presence of these hard bits and protons and so on, that might be something connected to QCD and this phenomenon of asymptotic freedom. It was not well understood. That was a thing which was kind of vaguely in the air, but it was a little bit kind of a few people at Harvard and Princeton knew about it, but other people didn't really know about it and believe in it, and so on. It was kind of in the air, but not very much in the air. And so then J-psi is discovered, particle is discovered, big sort of galvanization. What the heck is going on? Okay, one more piece of the history of particle physics that also plays into this. There was, okay, so back, we're talking, 1972, three types of quarks known: up quark, down quark, and strange quark. those are the three types of quarks. Those are the types of quarks where people had calculated based on those types of quarks, the electron-positron total cross-section would be such and such a value. Those are the quarks. We know what they are. Okay. Okay, there's another phenomenon. This relates to the weak interactions. So strange particles like the kaon, the lambda hyperons, all this kind of thing, these particles, so-called strange particles, that name was given to them by Murray Gell-Mann in the 1950s. Strange particles decay through the weak interaction. Wasn't really known how that worked back in those days. Again, there's a whole separate history to that. But in any case, there was, well, let's see, there was starting to be more understanding that the weak interactions might be associated with not photons, not gluons, but things called W particles. And also eventually things called Z particles. Okay, what okay, here's the basic point. In standard weak interactions, a strange particle, which contains a strange quark, or two strange quarks, or three strange quarks, but anyway, it contains at least one strange quark. It decays into things that don't contain strange quarks. And the process by which that happens, underlying process in terms of quarks, is a strange quark decays into an up quark with the emission of a virtual W particle, which turns into an electron and antineutrino, or a muon antineutrino, or whatever. But in any case, it's basically up quark, strange quark decays to up quark. Okay, things to know about this. An up quark has a charge of plus 2/3 of elementary unit of charge. The electron has a charge of -1 elementary units of charge. An up quark has charge plus 2/3 elementary units of charge. A strange quark and a down quark, they both have -1/3 elementary units of charge. That, by the way, was something very confusing about quarks, was people thought charge was quantized in units of the electron charge, because the electron and the proton have very accurately the same charge. 1 unit, proton is +1, electron is -1. And the idea that there could be things with fractional units of charge was confusing to people. In any case, big point, strange quark, mass charge -1/3, decays to up quark, charge plus 2/3, with the emission of a W plus particle, which turns into, let's say, a positron and a neutrino. Okay, that is my gosh, it's a long time since I thought about these things. When I was 13 years old, I wrote this whole kind of book-length treatise on weak interactions. Just a little bit too early, because it really wasn't talking about the kind of quark model of these things. That must have been 1973. But in any case, it takes me a little while to remember some of these things. Okay, so the basic point is that this weak interaction, strange quark decays into up quark, is a charge-changing weak interaction, in the sense that the strange quark has charge -1/3, the up quark has charge plus 2/3. Okay? Okay. So something that was never observed was a strange quark turning into a down quark. So strange quark has a mass, has a charge of -1/3, so does the down quark. So this was what became called the flavor-changing neutral current. So neutral current was, there's no electric charge associated with this. There's electrically, you've got the same charge in both cases. Flavor changing had to do with, do you go from being strange to not being strange? So no neutral currents, no flavor changing neutral currents, no were ever observed. So that was kind of a mystery, because it's like, why doesn't this exist? And there was a kind of one of the problems was, even if there's no direct way for some particle to get emitted, to go from the strange quark to the down quark or whatever, there should be something where there's a higher order effect, where there are kind of a combination of two W particles with loops of W particles and all kinds of fun things that happen in particle physics, that there should be a small rate at which strange quarks could turn into down quarks, but nothing had been observed. Okay, and the problem was that 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 should have been happening at a rate sort of higher than it was observed not to happen. So then an idea came up. There's a thing called the GIM mechanism. I think that's Glashow Iliopoulos Mayani. This was, when was this? Not sure actually, probably around 1970. Um, and the idea was, how about if there's another quark? How about, just like the strange quark has the same charge as the down quark, how about there's a fourth quark that got called the charm quark that has the same charge as the up quark? Okay, if that happened, it turns out that virtual loops of strange quarks and charm quarks and so on would cancel things out and make it be the case that you could explain why there was no strange quark goes to down quark decay process. Okay, so it's like maybe charm, maybe there's a new quark, maybe there's a fourth quark that exists. Okay, so then there was a paper, well-known paper called The Search for Charm. It was written by John Ellis, Mary Gaillard, and maybe some other people. That must have come out, oh gosh, I remember that coming out. So that must have been 1973 or so. It was written by people at CERN, Geneva. And it was just a catalog of, experimental ways you might detect these charm quarks. Okay, so, and I think in that paper they had mentioned the possibility of a particle that was a charm-anti-charm quark particle. Okay, so then the J psi is discovered. Nobody knows what it is. Lots of crazy theories. What sort of became clear, and I'm trying to remember how long it took. I think it was the idea that it was a charm-anti-charm combination was not kind of an immediate, well, it was, I think some people kind of thought that was the thing, within days, but that didn't diffuse out for a little while. Now, you should understand that the communication mechanism in those days, so, I was just a kid and my sort of communication mechanism was, reading, New Scientist magazine or something, a weekly magazine that still exists, or occasional things in newspapers. But then I guess I had also started getting preprints, which were a thing which is, big nowadays, but it was big way back in the day in particle physics. People would just write a paper and they would just send out copies to lots of research institutes and individuals and so on. So that was a pretty rapid communication mechanism that kind of went at the speed of mail, so to speak. So that was so people started putting out papers about quarkonium, which was kind of this quark anti-quark combination thing. And I would say that by early 1975, it was pretty much generally believed that this was a charm-anti-charm particle. And then the question was, could you observe a charm quark? Because this electron-positron total cross-section, that increase would have to be associated with the production of charm particles, production of particles that have not a charm-anti-charm combination, but a charm particle and, let's say, an anti-up quark. And so those things weren't observed for a little while later. Actually, I was a bit involved in that because let's see, this is now 1977. So okay, so the thing this whole thing about QCD is real, asymptotic freedom, that was kind of 1973, but that sort of gradually came in. By 1976, that was fairly accepted as a reasonable direction. So in 1977, for example, I was still just a kid, but I was working on, I got interested in QCD and started doing computations in QCD. I spent the summer at Argonne National Lab in the US, and got to use a computer there to do a bunch of calculations in QCD. And in particular, the calculation that I did had to do with how you could have gluons that were parts uh, of a proton, that gluon plus gluon could turn into a charm quark and an anti-charm quark. And so that was trying to calculate if you have two protons colliding, that you should get charm quarks produced at a certain rate. And so I worked out, based on QCD, there's a certain rate at which charm quarks should be produced. But they had never been observed. No charm particles have been observed in proton-proton collisions. They've been observed in electron-positron collisions, but not in proton-proton collisions. There was an experiment at Fermilab that said there just aren't charm particles produced at anything like the rate that I thought they should be produced at. Actually, that experiment was done using techniques that were a little bit going out of fashion at that time, emulsions, the things I mentioned before. And what those guys were doing was to look for little tracks for charm particles in their emulsion. Well, to know that to look for a track, the track has to be of a certain length. For that, you have to know what the decay, what the lifetime of the particle is. Actually, the lifetime that was guessed was wrong. And so they didn't see any tracks, but that wasn't because there weren't any tracks. It was because the tracks were, I think, a bit shorter than they thought, than they were looking for. So in any case, I was a little bit involved in that because I'd done this calculation of from QCD of the rate at which charm particles should be produced. Turns out in the end, the calculation was actually perfectly correct, and the experiment was the thing that was wrong, and that sort of got resolved in the next few years. But so that was kind of what happened, and I suppose what happened in particle physics at that time, just a lot of it's exciting, it's in the newspapers, it's things are happening. We've discovered a fundamentally new quark. Actually, I remember this must have been the summer of '77. There were two new particles discovered. The Tor lepton, which was very unheralded. It was kind of it's another thing like the electron, the muon, this thing called the Tor lepton, which has a mass of, see, now you can tell the things which were discovered when I was kind of leaving particle physics. I think it's 1.5 times the mass of the proton, give or take. In any case, the Tor lepton was discovered, I think, at an accelerator in Germany, DESI in Hamburg, and I think that's right. And then another thing was discovered. There was another peak was discovered at Fermilab. It was a peak at around 9.8 GeV, 9.8 times the mass of the proton, roughly. And that happened, I think, in the summer of '77, when Fermilab was sort of just down the road from Argonne, which was where I was. So this was big news, another big peak, and that became clear. So by the time people had known about the J psi, it was like that peak was called the upsilon particle. Leon Lederman was much involved in that discovery, and that was then it became clear that was another kind of quark. Nobody expected a fifth quark. Everybody thought four is enough. That kind of matches things. You don't get these flavor-changing neutral currents and so on. We're done. But then there was a fifth one, the B quark, and it was discovered about 5 times the mass of the proton. And then for many years, there was a big search for the top quark, the partner of the B quark, which turned out to have a mass of 170, 180 times the mass of the proton. Actually, again, I was that was discovered long after I was no longer sort of actively involved in the particle physics business. But actually, one thing that I was involved in, this must have been 1979. Okay, this is my last story for today. Probably I've been yakking on for too long here. That's a kind of a funny story in a way. So I was at Caltech, and I actually used to organize. This is 1979, so it was a little bit more of a grown up. But I used to organize the theoretical physics weekly seminars. And so it was a fairly small group of people kind of collected around a big conference table. It was myself and a whole bunch of people, including Dick Feynman. And who was uh, always quite, paid attention to what was being said and so on. Anyway, I'd invited this person, and this person gave this talk about Higgs particles and various things about interactions between Higgs particles and so on. And we're in the middle of this talk, and I'm realizing, wait a minute, there's something wrong here. This can't, this just doesn't quite make sense. If this, if this, then that, and then splat, more or less. And I have to say, at that time, Dick Feynman was very kind of, it was a rather competitive fellow in certain ways, and he would kind of delight in trying to see through, what's the fatal flaw in this presentation that's being given. Okay, so and he would kind of sort of roped me in as sort of a co-conspirator in figuring out what's the fatal flaw. It's kind of he was a lot older than me, and a lot more, should have been a lot more grown up. He was 3 times my age, but be that as it may. But in any case, and it would be, he would every so often in one of these talks, he would kind of look at me and he kind of like wink or something like, I figured out the fatal flaw, and then he would start asking a bunch of questions. Okay, so in this case, I had figured out something that I thought was kind of wrong, and I started asking these questions, and then Feynman, who was kind of, very much into this, was like really pounced and like that couldn't possibly be right to this person who was giving this talk. Well, okay, so it was sort of a weird thing about if you have very heavy quarks, all sorts of terrible things happen and the universe basically becomes unstable. Okay, so then I'm like, actually, this is a pretty interesting phenomenon, even though this, by the time it was clear there was something wrong with this talk, because there was something where I don't remember all the details of what was being said there, but it was something where sort of the thing falls apart for this kind of reason. Okay, so talk finishes and the speaker is kind of upset, and I'm, taking them out to dinner and so on, and that's all fine. I think that person had a successful career in finance, and probably that event in whatever it was, 1979 or so, might have pushed them over the edge of let's not do physics, let's do something else. And finance was just heating up at that time, so that might have been a great contribution to a career. But in any case, then I was like, this is an interesting phenomenon. And actually, I was talking to David Politzer, who was one of the other aforementioned characters, who was one of the discoverers of asymptotic freedom from 1973, who was then at Caltech. And we ended up writing this little paper about sort of the maximum mass that a quark could have in the standard model of physics without making the universe go unstable. And the bound that we got for that mass was around 200 GeV. So when the top quark was discovered with a mass very close to that, it was right on the edge. And it was like I was waiting to see whether, maybe there was something wrong with our argument, or maybe, the universe really was set up to be quite on the edge. I mean, there really can't be, if the things are set up with Higgs particles and things like that, the way that one thinks they're set up, then there can't be heavier quarks, or we have to explain why the universe didn't go unstable. So anyway, that's a little bit of that story. I think, okay, Jelly asks one question related to this. Why were quarks given such weird names like up, down, charm, strangeness, top, bottom? Well, it's an interesting question. Naming in physics was pretty sober up to probably Murray Gell-Mann's contributions, because he was the one that really introduced the notion of strangeness. That was very ironic, because Murray was a great lover of languages. I think his father had been a teacher of languages, and Murray had kind of picked up this kind of interest in many, many, many diverse languages, and was always fond of explaining that, so-and-so's name should not be pronounced this way, but should be pronounced in this completely bizarre way that was almost unsayable by somebody who only knew American phonemes or something. But in any case, there was some, he was very into words and languages and so on. So it is something of an irony that when he was a young fellow, he came up with this idea of strangeness, and he called it strangeness, which wasn't some nice Latin name that had some, complicated etymological story that Murray would have been very excited about. It was instead just this weird word. And that kind of launched this kind of tradition of calling things in physics by strange names. And I think that uh, that tradition continued for a while. I mean, I think in some ways physicists sort of realized that at some point this doesn't make our field look particularly good. It just makes it seem kind of silly. I mean, I would say that the up quark and down quark, that naming was a late 1970s naming. As I say before, I think they were mostly called P quark and N quark, um, or they weren't really given many names. Um, Charm, who invented that name? Uh, a European, but I don't remember which of the various groups invented that name. Um, the um, you know, people, well, the bottom quark, top quark, people were at one point it was the beauty quark and the truth quark, but then it became the bottom quark and the top quark. Uh, I think, this thing about names in different areas, it's like, oh, we're going to spend $10 billion on this particle accelerator to discover charm. Well, that doesn't, that sort of sounds a bit unconvincing. I mean, there are fields where this happens. Like, for example, in genetics, there are people gave all kinds of funky names to uh, to various genes. One that comes to mind is the sonic hedgehog gene, which is an important gene that controls development. And then uh, um, people realized that there were some kids that were born with defects in that particular gene, and it just wasn't good to say, there's a problem with your sonic hedgehog gene, so those genes got called SH. And I think in particle physics, they would have been well served by doing those kinds of things. Okay, apparently we should wrap up because in addition to me being late at our headquarters in Illinois, there are tornado sirens going off. I'm 1,000 miles away from that, so and I can't. So I'm not there, but some of us involved with this stream are there. So I hope nothing goes. I hope the tornadoes stay away. And thank you all for joining me. And I look forward to chatting another time. Bye for now.